Before we discuss how to compute confidence interval for variance and standard deviation, let me introduce a new distribution. So far, you remember you know already three distributions. We started with uniform distribution, which is the simplest one. Then we discussed a lot normal distribution, which is probably the most widely used distribution in statistics. And then now we also know approximation of normal distribution for small sample size, which we call a t-distribution or student's t-distribution, right? So now it's time for learning a new distribution, which is called a chi-square distribution. So let's recall the normal distribution again. So when we have normal distribution, we usually use standardized normal distribution. It's a distribution of z-scores. And then you remember that the average of distribution of z-scores is 0, and variance is 1, and the standard deviation is also 1. That's why we call it standardized. You remember we can test it by computing, for example, by using simulations, computer simulations. In this case, you can see I take a lot of z-scores. In this case, I have 10 million of z-scores randomly taken from the population. And if I make a histogram, you can see that indeed the histogram shows me that the average is 0. And then you can see that most of the values goes plus minus 2 standard deviations, 95% of the values, 95.5% of the values, okay? We also know something about distribution of sum of z-scores, right? So we know that if we take a sum of z-scores, then this distribution will have average also 0, but variance will be equal to n, and therefore standard deviation will be equal to square root of n. That's what we discussed in one of the first videos in this learning sequence, right? So this is what you already know. Now let's try to think on other situations. What if we take, for example, difference? So what will be the average and the variance of the difference of z-scores? Well, in this case, is it summation or it's a difference? Is it addition or it's a difference? It doesn't matter because it's actually the same operation. But in case of difference, you also multiply everything to minus 1. And since z-score is absolutely symmetric, so minus 2 turns to 2 and 2 turns to minus 2, then it doesn't change anything. So the distribution of the difference of z-scores is the same as the distribution of the sum of z-scores. So you can see it's identical, okay? But what if we think about sum of squares of z-scores? So remember, z-score is a distance. What if we take a sum of squared distances? So in this case, it's definitely not will be a normal distribution because we have non-linear transformation in this case, and we have no idea how it looks like. So let's discuss this situation. So first of all, I'm going to make a distribution histogram. I take 10 million values. You can see I have 3 samples, 3 large samples, just like 3 populations, right? Taken from with the same characteristics, with the same parameters. So it's just a standardized normal distribution. And then you can see that I don't compute distribution for sum of them. I take squares of all of them and then take a sum. So it's a sum of squared values. It's a sum of squared distances. And this is how distribution looks like. It's definitely not a normal distribution. You can see it's skewed. You can see it's non-negative because we square z-scores, right? So let's discuss distribution of sum of z-scores. Here I have sum of 2 z-scores, distribution of sum of 2 z-scores. So I have z1, which consists of 10 million values. I have z2, which consists of 10 million values. And then I take a sum of this, sum of squares of z1 and z2. Here I sum 4 z-scores. Here I sum 8 z-scores, and here I sum 10 z-scores. So you can see that the larger sample size is, the less skewed the distribution is, but still, even with 10 values, you can see it's still skewed, right? And it's still non-negative. That's normal because we have a sum of squares. And it's kind of looks like it's getting closer and closer and closer to normal distribution, but still it's not symmetric, right? So this distribution definitely not a normal distribution, and now we know that it depends also on the number of values or on the degrees of freedom. The sum of n squared z-scores we will give it a special name, which is called a chi-square. It's also a statistic. So sum of squared z-scores we will call a chi-square. It's a new statistic that we have. And this chi-square statistic has its own theoretical distribution, which is called chi-square distribution. It depends only on one value in the standardized form. It's degrees of freedom. It's a number of independent z-scores that we have. So for example, if we take all these n z-scores independently from the population, then we will have n degrees of freedom. But if we compute them based on the sample, then we will have n minus 1 degrees of freedom. We will discuss it in this video. Okay. So what you see here, you can see the theoretical PDF functions for chi-square distribution of different degrees of freedom. So here you can see the degrees of freedom is 4. Here you can see the degrees of freedom at 6, 10 degrees of freedom, 30 degrees of freedom, and so on. Okay. So this is some summary. So this is a distribution of sum of squared z-scores, never negative, depends only on degrees of freedom, and the expected value, so if you compute average, then it will be the degrees of freedom itself. So for example, if you have a sum of 30 z-scores, the average will be also, the expected average, the theoretical average, will also be 30. Again, as any theoretical distribution in R, we have these 4 main functions: the function that gives you random values, the function that gives you densities, probabilities, and the quantiles, and the same idea. So you have a name of the function, which depends on what you want to do, and then the name of the distribution. In this case, the short name is called CHISC or chi-sq. So it's a chi-square distribution. So it means that you can do all the things that you have done before with other distributions in case of chi-square distribution as well. And that just an example, right? So you can see that I took 1 million random values from chi-square distribution from population with 3 degrees of freedom. So degrees of freedom is 3. And then I compute average of these 1 million values, and I got 3. You remember, because you remember that the expected value, the average of all these values, it's the same as degrees of freedom, and that's what we got here. Okay. This is another example where I, instead of taking random value from chi-square distribution, I take 3 samples from normal distribution, 3 set of z-scores from normal distribution, and if I take a sum of these 3 z-scores, square it, I got 3 again, because you remember that chi-square, it's exactly a sum of z-scores. So from that point of view, it doesn't matter if you use R-CHISC function to get 1 million, for example, chi-square values, or we take 1 million of z-scores 3 times and then take a sum of their squares. It's the same, because chi-square is exactly sum of squared z-scores. Okay. And here I took the distribution histogram I started with for different degrees of freedom, and then I also added the theoretical PDF function on top of these distribution histograms, and then you can see it matches perfectly the empirical distribution. So indeed, the PDF function describes this behavior very well. Okay. The chi-square distribution is non-symmetric, it's skewed. So therefore, in this case, you cannot use this plus-minus error margin if you compute intervals, because in this case, you have to compute the left boundary and the right boundary independently. And then if you use chi-square distribution for confidence intervals, you need to do it also separately. So you cannot use just plus-minus error margin. And then how to compute these boundaries? It's the same like you do it for normal distribution and for t-distribution. You use the quantile function, the ICDF function, and then you provide probability to get on the left, right? So the probability that you have on the left to get a value smaller than this one. So that gives you the left value, the left score for the left interval, for the left part of your interval. And then if you compute it for the right probability to get a value smaller than this one, it's 975 in case of 95% interval, you will get the right score, the score for the right tail of your interval. Okay. And then, for example, let me show you. I take 9 z-scores and take a sum of them, of their squares, and I got 12.7. And you can see 12.7 will be somewhere here, right? So every time I get a new one, I will get value here, 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 here. So 95% of the cases, this sum of z-scores will be inside this. And then in 5% of the cases, it will be either here or here. So that's the meaning of this interval. And you can see that this is 9 degrees of freedom I have here, right? This is just a new example. So you can see that, again, I took 9 z-scores, compute sum of their squares. Then you can see I got 4, which is, you can see, a little bit larger than this one. So it will be somewhere here, 4. So that's the idea of this interval. So because z-scores are random numbers, sum of their squares also random number. And chi-square describes this random number, sum of the squared z-scores. So this is an overview of all distributions we know so far. We have normal distribution, which we use for the description of large number of random independent values. It has a standard score of z, it has standardized normal distribution, has expected value 0, and this is what we use it for, to describe behavior of random values inside population, right? We have students t distribution, which is approximation of normal distribution for small sample size. The standard score is t, and expected value is also 0. And what we use it for describing behavior of sample statistics which follow normal distribution, like average, regression coefficients, and so on. We cannot use normal distribution because we don't know the population parameter, so we use t distribution as approximation if sample size is small. And then we also know the chi-square distribution. The chi-square distribution, it describes distribution of sum of squared z-scores. The standard score is called chi-square. The expected value is degrees of freedom. And that's what we use it for. We use it to describe behavior of sample statistics that are computed based on sum of squares. For example, variance. And that's what we are going to talk about in the next video. Of course, what is missing here is uniform distribution, but we are not going to use it very often. So therefore, these are three main distributions we know so far. Normal distribution for large populations, students t distribution for small sample size, and chi-square distribution for sum of squared z-scores. In the next video, we will discuss how to use chi-square distribution for computing confidence intervals for variance and for standard deviation.